overview, since I have like 16 seconds to do this entire presentation. It's great. Software manufacturing systems, of course, very easy topic to cover. It only takes me about 2 minutes. So I'm to connect the ISO, it's an ANSI standard, been around for about 15 years. It's a subsidiary of AMT, and they facilitate the standard 513C. We've got probably over 150,000 places or machines currently with them to connect support globally, and 400 members, lots of work, lots of data, lots of standards that we also harmonize with. These are all the other groups that we work with. IOF, OAG, of course, IPC, Mimosa, ROS, ASME, QIF, yada, yada, yada. So we've looked at IOF as one way to maybe bridge some of these discontinuities as well. Done a lot of research. ROS2, we currently in NIST cell down at CCAM, which is doing some of the work that I'm going to talk about today. SpecOps was a dynamic scheduling project that we did with DMDAI, now MXD, O3 another one for in-process metrology and testing, and then the SMS testbed, which was funded by NIST, and basically installed them to connect on all their machines, but has not been upgraded because, well, it's NIST. So multiple pieces of equipment in the factory. Of course, you need to be able to harmonize or have a standard way of being able to describe the context and meaning of data you get off of machines. Machines give off a bunch of crap. You need to turn it into some kind of semantics, which is the common state and common vocabulary. So that's what we do. We normalize all the vocabulary, all the states, all the units, and contextualize it within the components of the machine, have a standard way of breaking down the machine into its components and its various different capabilities, and then we can do reasoning on them. We can also give the specifications and various other aspects of the manufacturing equipment. Of course, when you're going through sort of an analysis loop, you need to first collect data, then you need to what's called centrifusion, where you need to have a common timestamp across all the data that you're collecting, so you can do some kind of causal analysis of it. Then you can tag it with what it, just some syntax of key value pair. Then you can start turning it into contextualized data around the various different components in the breakdown of the machine. And then you can also give it names like positions and loads and rotary velocity, everything well defined, everything within the standard. So the standard standardizes the units, the states, and all these various aspects of it. The next thing is you can go to context. This is basically interval context based on combining various different aspects that you're getting out of the machine and then turning into higher level abstractions. What you need to do before you can start bringing it into your business systems, and then doing your predictive and prescriptive analytics on it. Because if you don't do this step here, you ain't gonna get to there. And this is actually a standard sort of pipeline of information transformations that you need to do. And what I found is that when people skip like this step here, go right over to a data lake, they get a complete mess, and then they spend all their time trying to figure out, oh, that was a position that was in millimeters. So, after remember one project, after about a year, they were able to, figure out the stack lights. So, clever guys. Anyway, so a lot of our use cases, scheduling, predictive maintenance, process analytics, machine monitoring, lights out manufacturing. We now use the word digital twin, though it doesn't mean anything, but anyway, we do digital twins. Like everybody else, because you have to. You don't want to be not that cool. But we do digital twins as well of machines, basically. I can even show you one. And the other two that actually I forgot to put on here, but the two that we're tracing now are certificates of compliance and certificates of completion, which actually are much more interesting in digital twin. So that's when you ask somebody to do something for you, even within your own shop, did they do everything that they said they were going to do? So that means that not just like machining operations, but it also means things like heat treat, ball peening, coatings, all the rest of those steps. Some of them non-geometric, some of them geometric, some of them. And were those tested? Were they verified? Did they verify everything? Did they miss a hole? all those kind of things. So how do you then map back all the geometry and everything else back to the original models and the initial intent? So those are two use cases that are being driven from our buddy over at Lockheed, Jan Denijs, who is trying to get a way to get that complete digital thread, which will tell him that his suppliers and his shops have done everything that's necessary to this part before it goes into assembly, and before they find that there's some problem with like a flight critical part, like a bulkhead. He said, if that thing blows out, bad things happen. So a very important thing, very important for aerospace especially. MTNIC went down the model-based standards development process a while ago. We used to be, basically a PDF-based standard like a lot of the others out there, and we recently just made SysML model normative. So basically everything is an XMI is our normative document now. We have a portal where you can explore the model. We also generate PDFs because, hey, people still like paper. We also have XSD, JSON, we have a whole bunch of different protocols that we support. We decided to take this standard and make it so we were a communication standard as well, so we could get data off the machines using REST, but we, a long time ago, divorced ourselves from representation and protocol. So we also have an OPC UA companion spec, we support MQTT, we're going to support SparkPlug-B and trying to do the first companion specification with SparkPlug-B, see if we can get them to do that. So the whole idea is it doesn't matter how the data is represented, it doesn't matter how you get the data from the equipment. What does matter is that it adheres to some kind of semantics, meaning, and structure and context. If you have that, then you can do fun things with it. If you can't, then it's basically useless, but you shouldn't limit the application's usability of the data. So these are, basically our models, where one thing that you find when you actually start doing full model base is that you can actually express a lot more in the model than you could even in documentation. So a lot of the relationships weren't possible before, or they were just confusing, but now we can actually do that. We've even pushed out some higher level abstractions, and that's one thing that we're actually doing. We're looking at for some of the ontological work is we want to be able to take those abstractions and then tie them into some of the terminology through an ontological layer, which is going to be sort of orthogonal to the information model, and is going to tie those terms to the other terms and to other standards that we're trying to harmonize, like QIF or measurement and verification. So we're working on what exactly that looks like in the models. So we're looking at sort of the whole Cameo suite of tools to be able to drive some of that concept modeling. Basically, we're using the concept modeler. Fortunately, it doesn't really deal with core and BFO all that well because of the way some of bits and pieces are structured. So we try to work around some of that. But the idea is to be able to build that sort of onto layer on top of this thing. And the other nice thing about when you go full model base is you don't just do information modeling, but you can also do behavioral modeling. So we can model some of this, these are like interaction models between request response for device interactions, which we'll talk about in a minute. And we can model the full state machines. We can also model the interaction. So we can do full simulation within the model of the interactions between multiple different machines. We can now model things like kinematic behavior of machines, because we have kinematic model. And a little, fun things like that, which before this, no way to do that. So it really opens up your possibilities. Also gives you ways of being able to create things like use case documentation and activity diagrams and all kinds of other fun things that really drive the standards development. And there really is no one single model, so it's all about the harmonization process. And what we're looking at is how we compose these various models together. A lot of them are going SysML. That's why we chose it. Like the CAXIF group with step 10303 is moving in that direction as well. Some of the APs, like AP242, has a SysML model right now. So there are intersection points. We can intersect at the SysML model layer, but we can also looking at, if you can build an onto layer on top of that, can you then also harmonize in other places? We're trying to convince some other standards to kind of do something very similar to this. So as actually the self-aware piece of this talk is around a project that we did This is auto. So around some work that we did with Ross Industrial and Southwestern Research Institute, QIF, and a few other companies. The idea was to create a autonomous cell that could use choreography models, which are basically a set of choreography and orchestration. Orchestration is where you have top-down control, and choreography is where you have a bunch of machines that are self-aware, and they talk about what tasks they want to complete. And using observation-based models, so we don't tell anybody exactly what to do, we just say, this is what I need done, who can help me do that? You can then make it all work. So it's reasoning on capabilities. Each of the machines knows their capabilities, knows what they're able to do at this moment, knows what the jobs are that they need to, that are they're being asked to do, and then they look at how they can figure this whole thing out. And the whole idea was that you have these, like, even the tables and the conveyor. We had like a table with parts on it. The table was intelligent, knew how many parts, it knew how many parts were in the buffer, how many parts were coming in, that kind of thing. Actually, we had a buffer separate. This is like, so, the table was actually the one who initiated the thing. So a table has a part. We always said, okay, the thing that has, so the initiator is the one that currently has part. And then it says, okay, I need a CNC and a robot to do this. And then the robot says, okay, I need a machine and a robot and a CMM. And then everybody kind of talks about what they need to have done. And eventually, everybody chooses what tasks they're going to do based on, we used a weighting mechanism based on the machine hour rate of the machine. So of course, machine tool always won. But then you had ways of being able to get out of starvation, where you could do priority elevation based on time. And we looked at some bad actor scenarios and a whole bunch of other things around this. Actually, the system behaved very nicely. We could drop machines in and out, and it would recover. So you could kill a machine. We had tool break scenarios. We had, robot failure. This did a project after this one where they had a robot failure scenario where they swapped out a human for a robot. It's kind of interesting that the model still works. So you can take the same task model and prompt a person with the same task level abstractions, and they're able to do things like loading a machine. Amazing. But the whole idea was that you could degrade it. You could degrade the performance of the cell without losing the functionality of it. So it's not like where you have central control where the cell controller dies and suddenly everything dies, or one machine dies and you can't recover. This was very fluid in the way it could recover and behave. So the other things we were working on were things like, you had slowdowns, or your buffer was full, or some back pressure through the system would cause it to then have to reroute or move parts around. Like your buffer's full, you could add another table. You can make changes to the system dynamically, and as long as the other machines were aware of what was in its vicinity, it was basically, it would still work. So cool things. We were looking at then how to scale this. So the next project, which never actually got funded because I wanted to say, was to say, okay, can we take the same model and go to the, this is actually part of a larger presentation, but whatever. Can we take this model and scale it to a line, a factory, an enterprise, and do the same semantics work? Can you use this kind of choreography model in large? And when does top-down scheduling work better than like a bottom-up or a choreography model? And where is there a breaking point? How do these things behave when you start even getting to like supply chain or anything else? So that was kind of our question: is how much, how far can you push this concept of distributed intelligence, self-aware equipment, or self-aware factories? Can you get composable? We were talking about this a second ago. Can you get composable capability all the way up to the enterprise level and still make it work? I don't know. We need to see. But it's kind of a cool idea. The other areas that we were working on was sort of this modular manufacturing capability box. So like, machines in the box. So could you, like, you have computers in the box, like Google does it, a whole bunch of other like cloud computing systems are, basic containers full of computers. could you do something very similar with, like, a container full of machines and sell a box capability? So I want to become part of a manufacturing network, but I need a certain set of capabilities. Can you do this either as a shared benefit, shared outcome type model where, this could work? Something interesting about that, we were playing around. There's a NIST cell over at CCAM, which is the Commonwealth Center for Advanced Manufacturing in Southern Virginia, that is currently playing around with some of this stuff. So this the concept, they instantiated the cell that we created before, and now they're playing on with extending it out a bit. Okay, yeah. I got a couple more slides. I'm trying to go really back. So the next piece of this is basically also being able to reason on then the design and manufacturing strategies. I mean, can you then take this further and say, okay, can you look at like an additive versus subtractive process and see whether you could swap it out given a set of constraints and what's available, location, environmentally, whatever. What is the most effective way of being able to make a certain part? Lastly, yeah, so this is, some links and other nonsense around the standard. There's a raw side talk around this thing that's in the bottom link, and I can send these out later. And that's it.
Thank you.
Can I make time? 16 minutes. Pretty close.
That's perfect. Any questions from the room? Yeah.
I have one.
Yeah, sure.
At the beginning of your slides, you had a step of adding semantics. I was wondering what general flavor of semantics you usually use. So I would expect, since we're onto comments, usually the ontologies and RDF. Is that assumption right?
No, I mean this was just started out as a pure information model, and but we were fairly rigorous about creating clear and unambiguous definitions and working around a few top-level abstractions. I mean, before we even went the Onto route. So, the idea that you broke a machine down into components, even though people like components, is probably better to use a word like systems. But you broke it down into parts, so there was a mereology about it. And then basically each of those components can observe certain pieces of data about themselves. That was the base concept. And there's this basically hierarchical breakdown of parts, and they're categorized. And then we were able to also lock down control vocabularies for all the states. So, and that is very rigorously adhered to in the standard. Things along that line. It's extensible, but at the same time, we have this sort of base set of information that almost every vendor has implemented. And that allows, for economies of scale. Yeah, sure.
You said normalize. I mean, was that in a loose sense? You don't have an algorithmically method for getting to canonical form, or I'm just assuming, you're just checking. I wouldn't expect you to, but I just wanted.
What do you mean by algorithmic?
The machine can do it.
No, because machines, they're dumb. But there is middleware, there's open source middleware technology that can do that. So there's, we provide an open source agent which effectively gives you that the protocol, and also maps the data from the incoming data sources to the information model. And it's got much more sophisticated recently, but there's sort of an adapter. I didn't have time for those slides, but there's sort of an adapter agent architecture, which then feeds that data forward. So, and the thing is that people have written, there's hundreds of adapters out there from various different third parties. There's open source ones. And it's we support like OPC UA native coming in, QTT coming in, and then do transformation scripting and a new agent to get your data into shape, validated, and then it's available upstream. So you can kind of create your own data pipeline, and that gets you your semantic layer. You're basically your context and meaning of the data, which you can then do more processing wherever. We're going to do some more work on some of the edge tech as well to see if we can You know, because some of the contextualization around like interval analysis we were talking about before, that we want to get onto the edge as well.
Thank you.
Yep.
Now we have Barry Smith with digital twins and the problem of model-induced escape. Take it away.
Thank you. So I published this book just last month with a colleague, Jobst Landgräber, who owns an AI company in Germany. He's a mathematician, amongst other things, and he has been striving for many years to make AI work in a number of different areas. And he did succeed, but in the process, he learned a lot of lessons about where AI will not work. And he's now going around the world talking to companies who are being offered all kinds of opportunities that AI is supposed to bring, telling them that AI will not bring many of those opportunities for mathematical reasons. And I'm going to apply one simple lesson from the book to the case of digital twins. So the summary of the book is that AI succeeds in certain narrow areas, but wherever we're dealing with complex systems, for instance, human conversation, emulation, or stock market prediction, then the AI will fail. And the reason is model-induced escape. So let's suppose you have an AI algorithm which will help you get rich buying and selling stock. Then if you're successful, other market participants will exploit the information that you generate in order to make you fail. That's model-induced escape. The model itself creates the reasons for the model failing. Something similar happens with spam filters. If you have a really good spam filter, then the authors of spam will use that spam filter in order to create new and wonderful kinds of spam, and thereby render your spam filter no longer operative. So this has a consequence for digital twins, particularly where digital twins are designed to reflect the patterns of behavior on the part of people. This would apply also in other areas too. So the idea is that the very existence of a digital twin operating in relation to people's behavior patterns will lead to changes in those behavior patterns. It will lead to a change in the system. There will now be a digital twin inside that system. And so the digital twin will no longer be accurate because the digital twin does not accommodate this new feature of the system, which it's supposed to be a model of, namely that the digital twin itself is part of the system. Now, this is a very beautiful example of model-induced escape. Every digital twin, which reflects people's behavior at least, must always be no longer a twin as soon as it's installed. But now there are more substantial ways in which the digital twin will change behavior patterns. So there will be some who react to the knowledge that they are being monitored by a digital twin by protesting that their behavior is being monitored and thereby changing their behavior, perhaps in such a way as to deliberately undermine the digital twin. And these kinds of attitudes are nicely summarized in this book already from 1999. Now, there is a nice paper about all of these problems, which I recommend people who are interested in digital twins should read. He's particularly interested in those cases where digital twins will allow prediction of the future and implement optimal control of, for instance, people's behavior. And he agrees with me that in those cases, digital twins will likely fail for the reason that they're using AI, and the AI will likely fail for the reasons which I've explained. But digital twins will work where we're dealing with infrastructures, and these are his words now, and geographies which change very little over time. and for instance, in production plants or aircraft engines and so forth. And the final chapter of the book describes those cases where AI will work, and they are pretty much the same sorts of cases as the cases where digital twins will work. So we believe that there is still a huge opportunity for AI and indeed for digital twin technology, but it will not do any of the marvelous, wondrous things that some people imagine it will. All right, now, many people think that these problems can be solved if we can just collect enough data. And the main thesis of the book, the central chapters, which are quite mathematical in nature, we think they demonstrate that however much data you have, you still could not create algorithms with the sorts of predictive powers which would be needed to engineer an AI which would work in any complex system domain. That means weather, climate, seismic, as well as human behavior, animal behavior, bird behavior. So we will never have an AI system which can emulate the behavior of a parrot, for instance, or a rat, perhaps even a bacterium. And therefore, there will be problems with digital rivers and other climate and environment-based digital twin models that people are developing. So these are the examples of complex systems where digital twins won't work. And the simple systems have all of these mathematical properties. So they have a fixed, the solar system is the best example. They have a fixed set of element types, a fixed set of interaction types, gravity in this case. There is one relevant force, again, gravity. All processes are time reversal. That means we have ergodic phase spaces. And that is the crucial part of the book. AI will not work if you have non-ergodic phase spaces, because you will never collect representative sampling data to train your neural network if you do not have an ergodic phase space, because no subset of the data is representative of the whole space. That's what ergodicity means. I don't need to say any more, I think. So simple systems have these properties. Complex systems don't have those properties. They have new element types. For instance, adults are born, dictators arise. People start to hate digital twins. All of these are changes in the complex system which will affect the predictive power of the complex system. So complex systems are subject to continuous evolution. This is true of the stock market, it's true of traffic patterns in large cities, and it's true in the weather. All right, I think that's, so these are some examples, and these are the 7 properties, and these are the cases where these properties are satisfied or not satisfied, and I'll leave you with that. And I must remember to stop sharing my screen this time. So please give me a word when you want me to stop sharing.
Thank you so much. I don't know if we have any questions here.
Nobody else has one. I got one. I get the sense that the digital twins.
I don't know. Can you hear, Barry? Can you hear the question?
Hear, yes.
Okay.
So I get the sort of sense that digital twins, they break down in these complex systems, right? Would it be AI?
They cease to be twins. They become twins of former states of the complex system.
But wouldn't that still be useful in certain cases? So even if
yes, for doing history, but not for doing predictions, and not for doing control. So you can't use them to control the system that they are modeling. You can, of course, try and use them for control. You can use them for carrying out experiments. So an example is the digital twin of the traffic system of Singapore. The digital twin, no one was told about the digital twin, and so its existence did not change people's behavior, but the system was used to carry out experiments. So there were traffic problems because there were too many cars. The system was used to carry out experiments of the effects of raising the car purchase tax or the petrol tax, or of just limiting the number of cars which could be sold in any given year. These were different scenarios, and they wanted to test whether which of these scenarios would bring about the most effective solution to this gradually worsening traffic problem. So that would be an example where even old data is relevant, because you can use it to imagine future possible worlds and then draw policy conclusions. But then you're not using the digital twin as a digital twin of the present. That's irrelevant. You're using the digital twin as an experimental basis for carrying out hypothesis-driven science.
Yep, makes sense. Thank you.
Okay. Thank you so much. Then we can go on to the next speaker. I can't pronounce your name.
You're not the only one who has difficulty with that.
Sure.
Yeah, sure.
Sure.
It's got all the difficult words or parts of a Dutch name, I would say. So.
Okay, so let's start the presentation.
Are you selected? Fantastic. Yep. There we go.
Oh,
And now, of course, which screen will we go to?
wait, I don't know if I'm, no. I have first, wait. No, first we need to share here. No, Janet?
I'm in the middle. And full screen one.
This one?
No.
So we still not, yeah, okay. Ah,
The pressure is mounting.
Yeah.
Thank you.
very good.
Yep, is it sharing and everything?
Yes.
Right. Yeah, my name is Sjoerd Ronge. I'm a scientist at TNO, the Dutch Institute for Applied Research. Let's see if I can. There we go. Given the time span, I'll try to get through the introduction slides quickly. But one of the things we do is R&D of new technologies, including technologies such as digital twinning in industry applications. And then we also try to apply those in practice, right? So as one of the previous presentations was already about how this is, how some technologies are applied, we try to do a similar thing. We get our whole mission statement here, but basically I don't do this alone. It's 3,500-ish colleagues that work on this, and one of the things we're working on is industry, which is where I'm mainly involved in. However, digital twinning, whatever that might mean, I've heard some definitions already today, and even some discussions whether it would be useful to start with. But we do that in all sorts of domains. I think the one at the bottom left, maybe particularly neat to pick out. It's about the soil beneath our feet, especially in northern part of the Netherlands, in Groningen. Another beautiful Dutch word. But there we have been extracting natural gas for the past couple of decades, and now we're having earthquakes there, because of course we have some empty areas beneath the ground. So we've made models, digital twins, of the ground there to figure out exactly how much natural gas we can extract into the future and what that would lead to when it comes to additional earthquakes. And as you can imagine, that's quite a relevant topic right now to society because gas prices are quite high. At the same time, we are having an increasing amount of earthquakes in this province of the Netherlands. So that's the type of work we're doing. And then we have like, other digital twinning kind of examples throughout the organization. This one, I think, is the stereotypical one, right? The guy with the VR glasses and an exposed model of his cat model. Right, this is who I am. Background in ontology engineering, now data sharing, and semantics for industry. Let's get to my definition of digital twinning, which is also what sort of raised my question just now. Because I think we are all sort of in agreement that a digital twin is some kind of representation of a system, a replica. But I would say it only has to be good enough to take action, to plan something within a certain context. So it's not the goal to create a digital twin of an entire factory in one go and perfectly model everything in there. Same as how it's not our goal to create a perfect digital twin of exactly what's happening in the ground beneath Groningen with this natural gas extraction. All we really care about is will there be an earthquake, right? And there can be some leeway there in how accurate you have to be, for example. Well, then there's also a more formal definition, of course, by the Open Management group, which I think is somewhat related, right? It's again about this virtual or digital representation of a physical thing, which in some way has been tailored towards a specific application. Okay, so here we have some examples of what it means to be good enough, right? Representative enough. In the case of our earthquakes, we want to have some indication if there will be an earthquake. Does it necessarily matter if it will be 3.2 or 3.3 on the Richter scale, right? It should behave similarly, right? If there is an earthquake, our model should say so as well. We scoped, we're looking at the ground and not like the storms coming overhead. And then the level of detail, I think that's something we've been, has been hinted to quite a few times now, about scoping basically of your project, which is to say we care about maybe in which side of the province something will start to rumble, but not which corner of your house, right? And then timely, of course, in knowing approximately when things will happen. We see a beautiful visualization, which is the reason that my PowerPoint was so big.
Yeah.
So why would we want to use these digital twins? It's in general because you cannot or don't want to do things for real, right? I think that's also something we can all agree on, whether it's an expensive car or actually in this case a Lego car, which is not that expensive. Anyhow, sometimes you just don't want to do these things. But once again, if you're talking about earthquakes, there's no place in the planet with the exact same kind of soil composition, where we've also been extracting natural gas for a couple of decades now, where we just so happen to be able to experiment with what's happening in Groningen. So there we need something. In general, it's better, safer, cheaper, whatever, to do it digitally, right? Okay, so a whole bunch of introduction and definitions. Diving a little bit more into what digital twinning means within TNO and how we sort of try to give this very abstract marketing concept some, and make it a bit more tangible. What we in general try to do is make this an interdisciplinary endeavor. Right? We pull together experts from the field. I've written down a few here. You can imagine a seismologist being tagged on when you want to do earthquake analysis. And then me or one of my colleagues will join in this project to make sure all these disciplines sort of work together. And they come up with a model that's either reusable or at least interoperable, which some would call a digital twin according to some definitions, right? However, we work in IT, so one of the things that we spend a lot of time on is automating our own job away. Ideally, we do not want to get to a digital twinning expert being involved in these projects, but having tools available so all the actual experts on the domain can work together, and the easiest way for them to do so will result, coincidentally, in a digital twin. Diving down a little bit deeper into what makes up, at least for our projects, a digital twin. On the left here, we can see, so maybe a preface, but we've heard a lot of different ways that we're describing this, right? We have a digital twin, we do digital twinning, it's like a noun, a verb, whatever. Here we can see as a noun, right? We have a sort of a replica of a system, like a simulation of the ground, or maybe some AI system which models or whatever, traffic in Amsterdam. Then we have data feeding into that model, right? That would be the seismology sensors or the car traffic on the roads. And then we have an application built on top, which is usually what people will point to and say, that's my digital twin, because the first application is often the visualization of that data in the model, right? All of that stuff combined and developing that is what we would consider to be digital twinning, so sort of more the verb. But really it's about this, primarily about this simulation or model and making that connected with actual data coming in and applications built on top, what it's all about. I think a major part, or even the difference between this and simulation, would be that simulation I could make like an Excel, I can simulate something if I really want to, right? But that's probably not going to be interoperable with other systems. It's not going to be something I can just plug and play into my factory, for example. The idea is that here we're using open standardized technologies. We're building it on whatever kind of standard. We can reuse something. I'll quickly skip by this because I think it's been covered a few times, right? But you do these sort of things with the people intending to implement or to use the technologies. It's not something that people come up to us and say, we need a digital twin, and then we develop it and give it to them. That question does happen, right? see this flashy video of Industry 4.0 in which digital twin is presented as the best thing since sliced bread. They'll occasionally come to us and go like, we need this. Okay, let us start at the beginning, right? Everybody that comes to us, and I think all the projects that we've heard about today have sort of the same goal, right? It's either to make more money for a company or to create impact for society, or at least in some way have it being applied somewhere. To that end, right, I would like to take, if I have 2 more minutes, to look a little bit forward into where we're hopefully going. It says here, imagine a lights out factory. Usually in these kind of presentations, people have a hard time grasping this, but I've already heard the term lights out factory, dark factory, being dropped a few times. But let's imagine, right, a factory filled with all sorts of manufacturing equipment, sort of autonomously doing its thing. Doesn't really produce a product. It's not like a car factory or a bicycle factory, just a generic factory. And it provides capacity to whoever needs it whenever, right? So for example, if you suddenly need a lot of face masks as the pandemic strikes, a face mask manufacturer probably doesn't have the capacity to supply that. Instead, they would call up this lights out factory and say, could you help me out for the foreseeable couple of months? You can imagine the operation of such a plant would be incredibly difficult, right? You have a great variety of products coming in, and you continuously have to match your needs when it comes to producing these with the machines that you have available. So quite a complicated endeavor. In my mind, the solution to this sort of boils down to interoperability, right? We can make digital twins of these machines and these products, and all of that. But what we need is a way for them to understand each other. Right? The factory needs to understand the orders coming in and how to manufacture these. It needs to model when it could manufacture this, if at all, and simulate how it would do that given the machines available. So a lot of complicated challenges to tackle. I know of at least one project that we're involved with, which is already starting with this very slowly, called the Eureka Project. This is one of the large Horizon Europe projects, so some of you may have heard of it. It doesn't go completely to the looking forward vision, right? But it's taking some steps in that direction. Okay. Boiling it down a little bit to what we are working on and what I think we, like all of us, could be working on, because at least what we really need is, well, digital twins, obviously, that's the name of the presentation. But that's a bit of a cop-out. So a little bit more concrete, we want to have some tools to develop these digital twins, right? I want to automate away with my own job, if not just making it a little bit simpler. What does that then mean? Right? Really, we need tools that work with the technologies that go into such a digital twin. So in the domain of industry, we use quite often something called the asset administration shell. It's a semantic modeling paradigm for to represent data, for example. Just how most of us here, I think, would use RDF for ontologies. But for the asset administration shell, there's almost no tools available right now. It's even worse than it is for RDF, basically. And so we are working on developing tools for that sort of thing. That's one example, right? Tools for interoperable data models, but it is also needed for reusable simulations or model-driven applications. I think a lot of the projects being mentioned here actually today are already sort of working towards this. And I'm hoping that we can reuse that to make our job a little bit easier. Okay, then to wrap up, some of the, to make it a bit more specific, what at least within TNO we are working on. We're working specifically for this asset administration shell on a couple of things, like a connection with more legacy systems and development methodologies, which apply more to modeling in industry in general. We have connections to RDF ontologies, so two meta languages that we map onto each other. And then on the left there, we have a couple of projects going on. Master AI one will be interesting because the example, William, you gave about this like plug and play production cell is something that this project sort of tries to work towards. So I'm happy to hear that it's already there. That means my job is done, hopefully.
We don't have a digital twin now.
Sorry?
We don't have a digital twin though.
No, I mean that's we can write something for that, sure. No, but yeah, lots of projects, both large European projects, as well as smaller, like company-driven initiatives that are going on. And the sort of overarching theme for them, at least from our development and research perspective, is that we do some research on what it means to be a digital twin, try to answer some of the questions like digital twin can never work for a complex environment and tackle those. and in part develop tools to make it more accessible to people working with whatever set of tools you want to consider for digital twin. I think if we still have time for a discussion, my question to you would be, are you already doing something in this field? And especially some of the people that haven't yet presented. If we don't have time, then I suppose my last slide would be get in touch. That's it. Yeah.
Go.
I haven't asked many questions during these days, and I didn't speak either, so I think most people know what I have. So I can see what I'm doing. I can ask a question as well. So I'm working with digital twins as a software engineer, so I'm building such the same thing that we're talking about here, and especially in two problem areas I want to raise. So the reason why I'm here is because we are a demonstrative project called Wasserfall, and we are working with the supply chain, connecting the wood value supply chain to wooden building. So we are working on the whole wood process industry, how that goes, and into the manufacturing of sustainable building products, and then into the building construction, the building life cycle, so the whole maintenance phase. So basically, so much things that are covered here are so relevant. But it's a challenge because these are thought of, they are not practical now, but they are thought of like digital twin actors along the supply chain. So that this makes the chain of twins or systems of systems thing. In another thing I'm involved in is the Digital Twin City Center. It's a Swedish project hosted by Chalmers that is working on the national digital twin, just like you have and countries have, like the UK national twin. Yeah, and there's also this kind of idea there that we are what is digital twin, and we're starting to ask where we're collecting data and we're putting data somewhere. And we know that we have a system of systems approach problem. Like we have things that are systems and systems are part of systems, and these need to be autonomous and they need to be connected to each other. And there's like a challenge. One of the things I'm curious about here is what we are talking about in this conference. There's something that can help to glue this together that week, because it's like very. But my question is like, do we have any ideas on resolve this in some kind of way?
It's I think a tricky question, right? And at least as far as I know, like the jury is still out on how best to go about this. But in some of the projects that we're doing, I'm seeing a couple of different approaches, right? You can say we have a bunch of like individual systems, and they just need to be interoperable with all of these other individual systems.
Interchangeable, like
exactly.
Someone
yeah.
can replace a system for another system if they have exactly the same kind of definition.
That's sort of I think built on like multi-agent system theory as well, right? You have these more or less disjointed pieces of logic.
Many systems, I'm looking in the future. I mean, if we are digitalizing, what will happen? We will not have less systems.
No.
Like you have more and more digital twins.
Yes.
Yeah. Whatever you call it, like digitalized machines or whatever, things that are connected to each other. So,
yeah. It's tricky, right? Like I don't think like back when we usually would have some hierarchical structure for this, with some top level piece of logic which controls a bunch of agents or actors beneath that. That seems to be breaking down when you get this many new systems popping up, right? So it's really at least the angle that we're tackling it from is interoperability, both on a technical sense, that they're able to technically exchange data, such as some protocol that you're using, as well as semantically, that they use the same information model, or at least information models which have like a linking concept that connects them together. So it's it's difficult challenge. If you have solution ideas, then shoot me an email.
It's just different domains that need to connect to each other. How to scale it up so that it's easy to connect. So I haven't solved it, but we have to solve it, and we are doing it now. So this is our demonstrator. I mean, the supply chain. So it's stressful to. I mean, if we're going to be demonstrator, we need help with the solution. Otherwise, we cannot be a demonstrator. So if no one has the solution, or at least what we can do as first steps, so we can say that at least we tried this for this project, and then we know this.
Maybe, but that's maybe for during the coffee break or whatever is after this. But I can tell you a little bit about some project on the slide, the Smart Connected Supplier Network, where we did a sort of supply chain integration for metal manufacturing. It's not as much focus on traceability, but there may be some things you can reuse there. So.
Yeah.
And we definitely need from the Ontocommon side to really take a look at all the tools and methodologies that are being developed and see how we can apply that to such a case like yours, because I think it's really the problem that we need to solve and that we want to solve, but yeah. If there's no more questions.
I think that
Yeah. We out of time?
Yeah, I think we need to go to the
Yeah, what's next?
keynote.
Yeah, there's a keynote.
Mara,
Has it started yet?
Don't worry, the other is not finished.
Yeah, okay. Okay, then go ahead. Knock
Everybody's
yourselves out.
If you want to go ahead.
Okay, it's something that's bugging me. And there's one of your slides you talked about something about you have to have focus, and it strikes me as a sort of a manager's view to what you need to do to manage cost. And there's a quote from Herbert Simon I like about complex systems, and he says basically if you're dealing with a complex system, he says you can plan out 1 or 2 months if you want to. You can plan out 3 or 4 if you like risk. You plan out for 6 months or a year, any level of detail. He said you're just going to be wrong. It's just a waste of time. So it seemed to me that there's a better way of phrasing it would be individual projects should be cost justified, which is essentially you need to look at the benefits. But it'd be nice to have a long-term goal that says, look, these motherhood type stuff, that these look as though, and we can't guarantee it will be, but it seems to me, because in our ontology work, I think we've got a 10-year exercise. Now, I can't cost justify investment over 10 years, but I can cost justify, okay, we're agreed. But it would just be nice if I can persuade you to change that slide.
Yeah, I see. I'll take that. I'll take you up on that. So you're to some extent right that it's a bit of a managerial slide. It's a response to companies coming to us. We need a digital twin.
I thought his response to the government not wanting to give these companies any money would be my interpretation of it, but then that's okay.
So, yeah.
But I think you could just do 2 slides. You can say, look, every project should be cost justified, and that's okay. If I'm going to give you X, try and give me Y back. But it should be done in this context. This is a step for a bigger goal. And then I'm not trying to fight the managers. I mean, there's a reason they have a point. It's just that the more important point is this long-term goal. That would be my plan.
For sure. I think within our projects, we try to still work towards that long-term goal.
Yeah.
But usually the companies or the implementation places, they don't all care about that long-term goal, right? They want something now.
Okay, I see your problem. Okay.
There's
Okay,
in
so
general.
it depends on the audience. Then you have 2 versions of the slide,
exactly.
one for me and one for everyone else.
Yeah. William, did you have
Yeah, so I'm going to be the cynical person. So the whole term digital twin has really been kind of scaring me because I just because a couple of customers that were customers say about people who are working with some standards groups that I work with, they're jumping at digital twin as the savior of IoT and Industry 4.0 and every other buzzword that came before. Yeah. But what they're saying is that we don't need to do any of that. We don't need to do any of the data collection. Yeah. Somehow we're going to be able to just stand up these. We just create the digital twin. It's going to just kind of like materialize out of the ether. Boom.
Yeah.
And so stop collecting all that damn data.
Yeah.
You silly people. And we haven't solved the problems of industry. Basically, like I was with IIC before, and, did some IoT stuff, and, as we were calling it back in the day. And, then it got rebranded as Industry 4.0, and it's got branded. And it seems like we move through, we fail, and then they change the wording. But we had everything that we were presenting, like in IoT and IIC around like industrial analytics and industrial AI, and that whole thing was basically digital twin. There was no light between the two. We were just looking at how to get prescriptive and models and predictive analytics by collecting a lot of data, analyzing the data, building your learning models, iterating on the models, and so forth. So it's basically the same thing, but we didn't succeed mainly because we didn't do the upfront work of getting direct data in, curating it, and managing it correctly, I'm just wondering, what are we gonna do differently this time?
I mean, now I'm speaking like we are going. You're asking me what we are going to do differently. That's a lot of people, right? You can speak for everybody. Great.
Yeah, I claim that I'm a digital twin software engineer specifically, and I know why. Because I'm coming from different environments. So I have my background, not so much from the industry like the manufacturing industry. And the thing is that in the building industry, we are working a lot with like CAD models, and then we have recently embraced the IoT concept, like with sensors and stuff like that. So I think for me, it's a digital twin thing is a mental way of saying that now when we are doing something, we are from the beginning designing it in a sustainable way so that we can continue to maintain this model or system, because the model that we used before is a model that is something that is basically rendered and you can analyze and you can do whatever you want. But I think the twin is already somehow integrated into the real world, because we need the twin to be, like you say, I also agree with that. It's like a good enough representation of the reality that we need to solve a problem, and that needs to be kind of a living thing. It has to be reconnected. And we haven't solved that yet, I think, because ideally that should be automated. So we have a fresh digital twin every day or something like that, collected from things that go around and collect new data from the real world. So now there's a lot of manual things going on in digital twin where people actually load files into the digital twin or in proprietary systems they call it digital twin. Like this is what they call it. But I don't agree with that. But that is what we have, so we start there. So we have manual processes. Then we are really change it to automated processes to be digital twin and make it an updated model all the time.
Yeah, I guess that sort of speaks to my fear.
Okay.
Is that yeah, you kind of hit it right there, the manual processes and stuff. It's like we didn't. It sort of took the focus off of data ingest, curation, standardization, normalization of data up front, and that whole sort of front end process, which we said we were going to solve, and we didn't really solve because we kind of got distracted. We got distracted with the big picture. We didn't achieve that sort of big picture, predictive analytics first go around because we still, it's like, we get bored with the plumbing. So we don't want to do plumbing because plumbing is boring. We want to talk about pipes.
On this plumbing, right, on the interoperability basically between systems and between organizations, there's been quite a lot of development outside of industry, which we can now bring back into industry. I think ontologies and RDF are a decent example, right? When you go back 10 or 15 years, and
I think the metaphor is more about clearing the sewage out of plumbing rather than having pipes.
It's kind of we need to focus. I actually talked about this at IIC as well as some other groups. Is that I think we still need to focus on building robust data management architectures that can drive all this technology. Digital twin concept as it is fine, but if we don't, we take our eye off the ball of the feedback is key to a digital twin. Digital twins without data feedback from the real world doesn't really mean anything. You just got a simulation model like we had before. So it's just same animal. So if we don't fix that ingest issues that we had, we're gonna have to find another word.
Oh yeah, for me it doesn't matter if we are using some new buzzword. For me, the word is just a way for us to agree what we are talking about now. I wouldn't mind if there was a new better word.
There's a thing in psychology about you only have so much energy, and if you devote your energy to jumping up and down about a new word, you don't have enough energy to do work. I forget
So I think I agree. I think we talk about the same thing. Right?
Yeah.
I don't mind that we are working with. I think we're working with what we already have.
So I was at a conference, just one brief point, a week ago, and one of the guys from a big aerospace company, that's where I came up with that quote. I mean, he told me that we're doing digital twins now, so we can just forget about all the stupid data collection stuff.
Well, that will work.
Nice point.
And it was like,
Someone talked about this here, that Interoperability twin is just like a,
Container kind of.
call it whatever you want. I mean, in the end, we are talking about what we're talking about here. We are talking about what we're doing and what we did before. So I don't think it's a reason to be annoyed about new buzzwords. I am not that. I think it's the more.
if there was annoyed, I said frightened.
Yeah,
It's a different sphere.
A couple of years we'll be talking about something that's also smart. Right? It's,
Smart digital twin.
yeah.
It feels a little bit that we're redoing everything from scratch again, or everything, but many things, let's say like this.
Mhm.
And then again and again, I think that's your fear.
Reading the marketing, that would work.
Yeah, my fear is that we take the focus off of still fixing the problems that we haven't solved yet, because we think we have a new magic. It's like with AI and ML, right? It's like, oh, those are going to solve all the problems, but we just find out that okay, well, it's just fancy regression and
Yeah, because I'm not talking about a specific software at all.
Yeah.
And if I not do that, then we are back to the point again.
Yeah.
What we're discussing.
I think that's true.
I think so. Thank you so much. No, you're not anymore. Okay. Thank you. We're going now to the keynote speech.
Very sad.
Right?